Okay. So let's get into the nitty-gritty of conducting a hypothesis test. So this is going to be t-testing. All right, and so the way t-testing works is we wish to compare the means of two populations based on samples drawn from each population. Okay. We have a pair of hypotheses. Our null hypothesis is that mu1 equals to mu2, which can equivalently be written as mu1 minus mu2 equals to 0. And our alternative hypothesis is we replace the equal with either a greater than, less than, or not equal sign. And this is equivalent to writing that mu1 minus mu2 doesn't equal 0, is greater than 0, or is less than 0. Okay, so the null hypothesis always has the equal sign. The alternative is identical, except you replace the equal sign with something else. Okay, and we always use population parameters in the hypotheses. Or I get in the hypotheses. Okay, so never use y bar in the hypothesis. Okay, the data required for our test we need 6 pieces of data from sample 1 and from sample 2. We each need a sample size n1 and n2, the sample mean y bar 1 and y bar 2, and the sample standard deviation s1 and s2. Our standard error is the same standard error that we saw in confidence intervals for 2 samples, s1 squared over n1 plus s2 squared over n2, that quantity inside a square root. Okay. And we calculate essentially what's a z-score, except we call it a test statistic. And a test statistic is almost always in the form of what we observed minus what's expected divided by a standard error. Okay? So when we are talking about two populations, here, I'll let you guys finish writing all of this before I continue explaining things here. Okay, so when we're talking about two populations and two samples and using that to compare means, what we observe is we're observing a difference between means. So the observed value we see is y bar 1 minus y bar 2. This is the observed quantity that we see. Okay. If the null hypothesis were true, if this or this were true, or if this and this were true, what would we expect y bar 1 minus y bar 2 to be? We expect that difference to be 0. Okay, so our expected value is 0, so we would technically be subtracting off 0. And then we take this difference and we divide by our standard error. So I'm just going to write SE. Okay, because we're just subtracting off 0, I'm just going to write, effectively this becomes y bar 1 minus y bar 2 divided by our standard error. So this is our test statistic. Okay. And what we then do is we look up our test statistic, which we sometimes write as Ts, or just T, in the T table with degrees of freedom equal, and again this is an approximation, n1 plus n2 minus 2. And that's how you do it. So we'll do an example and we'll run through this, but I think it's a rather, the process itself is rather straightforward, okay? Oh, I'm sorry. So when you look up the test statistic in the T table, you get a degrees of freedom. I'm sorry, not you get a p-value. Okay, you get a p-value. And what do we then do with the p-value? To make our conclusion? How do we make a conclusion based on our p-value? Compare it to the alpha. We decide, is our p-value big or is our p-value small? To do that, we compare it to alpha. And if our p-value is deemed big, what do we do? Yeah, so the technical term is we have to say we do not reject the null hypothesis. We say we don't have evidence against the null. And if the p-value is small, we say we reject the null hypothesis. We have evidence against the null hypothesis. And you know, you said accept the null hypothesis, which technically as statisticians we are not allowed to say that, okay? So you can think of it as the way a jury, when they come to a conclusion, they never say we, the jury, find the defendant innocent. They always say we find the defendant guilty or not guilty, according to the charges or whatever. They never say the defendant is innocent, because a lack of evidence doesn't prove innocence, okay? And so in the same way, if we don't have enough evidence against the null, it doesn't prove that the null is true. And we'll talk about all of this maybe later. Okay, so let's try an example. We'll talk about using the T table because it's a little bit different than what we might be used to. And we'll do it. Okay, so let's see. Okay, so here we want to see, so we, here, sorry, example, this is 7.2.5, okay? So we grew a total of 15 plants. 8 were control plants, and 7 were exposed to ANSI, or used ANSI as instead of water. What is ANSI? Some other, something else, not water. Okay, and we measured how much they grew and the standard deviation. Okay, and so our data shows this. So control and ANSI, we have our N, our Y bar, and our S. So control, we had 8 plants, 15.9, standard deviation of 4.8. The ANSI grew 7, 11.0. And 4.7. Okay. The prior to the experiment, researchers just want to know, would ANSI cause a difference? Okay. Cause a difference in the height. Okay, notice we are not asking would ANSI cause them to be shorter, and we're not asking would ANSI cause them to be taller. We're just asking would ANSI cause a difference. Okay, this is not asking does ANSI cause them to be shorter. Okay, we're just asking, does ANSI cause a difference? So in this case, our null hypothesis would be that they're equal. This is pretty much always going to be your null hypothesis. And then the alternative, because we're asking does it cause a difference, we're going to use not equal sign. Okay? If we had asked does ANSI cause them to be shorter, cause the plants to be shorter, what would we use? If we control to be group 1 and ANSI to be group 2, we would expect mu1 minus mu2 to be greater than 0, okay? If the question was, does ANSI cause them to be shorter, okay? But in this case, because it's just asking, is there a difference in the height, we have this, which means we have a non-directional test, okay? So the not equal sign means non-directional test. Okay, so we're going to calculate our test statistic and then use this to get a p-value. Okay, so our test statistic will be y bar 1 minus y bar 2 over our standard error. And our standard error is the square root of s1 squared over n1 plus s2 squared over n2. So our standard error is 4.8 squared over 8 plus 4.7 squared over 7. My test statistic, whatever this number turns out to be, I'm going to plug that in, and our test statistic will be 15.9 minus 11.0 divided by our standard error. Sorry, let me get this in here. Okay, 4.8 squared divided by 8 plus 4.7 squared divided by 7. 6.0357. I'm going to take the square root of that number. My standard error is 2.457. So here I have 15.9 minus 11 divided by the answer. And I get a 1.994. This is okay. All right, and how many degrees of freedom would I use? So just as an approximation, we're going to use n1 plus n2 minus 2. So I'm going to have 13 degrees of freedom. Okay, so my test statistic is 1.994, and I have 13 degrees of freedom. I want to make sure everybody is with me before I move on into using the t-table. Everybody good? Okay, so if you have your t-table, pull those out. Okay, we're going to go to our t-table. We're going to go to the row 13 degrees of freedom. Okay. So we're in this row with 13 degrees of freedom, and our t, what is our t, is 1.994, right? So essentially what I'm doing is I'm saying, okay, I've got 1.994, I'm looking for where this value, 1.994, where does it fit in this lineup? It fits in between 1.899 and 2.060, so 1.994 fits right here. Can we see that? Between these two columns for row 13. Which means my tail probability will also be between these two columns. Okay? If the number I happen to have was 1.1, then I would say 1.1 is here and my tail is in between these two columns. And if I happen to have 0.5, then I only know one side of my tail, and that would be that it's on this side of the column. Or if my tail was, my test value was like 5, I would know that my tail goes over here. Is this okay? So I'm just finding where my test statistic is in this line, and then I say my tail probability is then between the column headings for those columns. See here, what I see is my test statistic is in between these two columns, therefore my tail must be between 0.03 and 0.04. Alright, so we'll go back to what we have here. And so what we say is that from the table, the corresponding tail is between 0.03 and 0.04. Okay. The t distribution is symmetric. So if you ever get a negative value, just drop the negative and look up the positive thing, okay? And so what this picture looks like, t distribution pretty much looks exactly like the normal distribution. It's just the tails are a little bit wider, okay? And so what this says is that, you know, at 1.994, if we shade everything in the tail, which means basically the part that goes away from the hill in the middle, the amount shaded here is between 0.03 to 0.04. We don't have an exact value. We just know that the amount in this tail is between 0.03 and 0.04. Is this visualization okay? And so keep in mind that we have a non-directional test. So what a non-directional test means, I'm interested in the positive difference. I would also be interested in the negative difference. So how much would exist in this tail over here on the negative, if I had negative 1.994? Well, this will also be between 0.03 to 0.04. And so what we have is that my p-value is equal to my total tail area. How much would I have in both tails combined? It's not an exact value, but I do know that that number has to be total tail area is between 0.06 and 0.08. Okay, or I can write my p-value is in between 0.06 and 0.08. I could write it also this way as well, right? Is this okay with everybody so far? All right, so can I flip to the next slide? Okay, so let's say our alpha, so on the previous page we said 0.06 is less than our p-value, which is less than 0.08. We don't have an exact number for our p-value, but we know it's in between these two numbers. Let's say we use alpha equal to 0.05. What is the conclusion we make? Our conclusion is, well, we say our p-value, is it bigger or smaller than alpha? It's bigger than alpha. So what do we say? Yeah, we do not reject the null hypothesis. Okay, or we say, in the context of our problem, we would say, we do not have evidence or have enough evidence to say that ANSI causes a difference in the height of plants. Is that okay? All right, I'm gonna do something. We're gonna kind of continue this same example, but we're just gonna change things just ever so slightly. All right. So let me go back here, and I'm gonna So using the same data, okay, so we're going to use the same data, but this time, okay, prior to collecting data, so this is the key. Prior to collecting data, researchers wanted to know does ANSI reduce plant height? Okay. So in this scenario, our null hypothesis would be mu1 minus mu2 equal to 0. And our alternative hypothesis would be that mu1 minus mu2 is what? Greater than 0. We're expecting the control plants to be taller than the ANSI plants. Is that okay? All right. And so when we calculate our test statistic, what would we end up getting? We end up getting the exact same thing as before. 15.9 minus 11.0 divided by our standard error, which, let me flip back, was 2.457. We're using the exact same data, right? Our test statistic ends up being positive 1.994. Okay, so same data as before. Our test statistic ends up here. Okay. We go to the t-table and we look this up with degrees of freedom equal to 13. All right. What do we get for our p-value this time? So this time our picture is a little bit different. In this case, because we're interested only in mu1 minus mu2 being greater than 0, in this case we only take the right tail. Okay? We only take the right tail because of the greater than sign means only go to the right. Okay, so our tail area is between 0.03 to 0.04. We only take the right side, so our p-value is between 0.03 and 0.04. Okay, or I could write 0.03 is less than our p-value is less than 0.04. Is this okay so far? All right. So what is the conclusion we make this time? Let's say our alpha is 0.05. Our conclusion is we reject the null hypothesis. Okay, and we say we do have evidence that ANSI reduces plant height. Okay. Now some of you might feel like you want to raise some objections here. Let's just do one more exactly like this. Okay, but I'm just going to flip something around, and then we'll talk about all of these differences in a moment here. Okay, so I'm going to do the exact same thing using the exact same data, except I'm just going to change one thing around one more time. Do we have all of this here? Okay, so last thing, same exact data, okay, except here we write prior to the experiment. Okay, so prior to gathering data, okay, researchers asked will antsy plants grow taller? Okay, and so in our case, our null hypothesis still exactly the same, mu1 minus mu2 equal to 0, and our alternative this time would be what? Mu1 minus mu2 less than 0. Okay, our test statistic ends up being exactly the same, 1.994. Degrees of freedom still 13. We draw our picture. Okay, and because we have the less than sign, we want the area to the left. Okay, so our tail is between 0.03 to 0.04, but our p-value is actually everything over on this side. So what is our p-value? My p-value is between 0.96 and 0.97. And that might feel absurdly high, and it is very high, but let's just kind of pause and think about what we're saying here. So prior to gathering the data, the researchers asked, will antsies inhibit, or will antsy plants grow taller than the control plants? Okay. When we look at our data, what do we see? We see that the antsy plants are shorter than the control plants. Okay, so are we going to have any evidence to support this notion here? No. Okay, so because our p-value is so big, we're going to have to say we have no evidence to reject the null. We have no evidence to support the notion that antsy plants grow taller. Okay. Remember, our p-value is what is the probability of observing our data or something more extreme if the null hypothesis were true. Okay? And in our case, more extreme would be data where the antsy plants grow taller than what we observed. Okay? So if the null hypothesis were true, what is the probability that we would see antsy plants growing taller than 11? Well, if the null hypothesis were true that that there's no difference, we would see quite a high probability that that the ANSI plants would grow taller. So in our case, we would have no evidence to support this notion that ANSI plants grow taller. Okay? So let's just comparing these. So with the two-tailed test, we're looking at both tails. So we find the area in one tail, and then we double it. With the one-tailed test, with a greater than sign, we always go the area to the right, and with a less than sign, we always go with the area to the left. There's this idea of checking directionality. So technically, I wouldn't even have to go through this entire test over here. With if prior to gathering the data, the researchers asked, will ANSI plants grow taller? I don't even actually have to go through this process. I can just look at my data and do what's called a directionality check. I can say, well, does the data I have could it possibly even support this notion? And just by looking and seeing 11 and 15.9, I can say, I'm not going to have any evidence to show that ANSI plants grow taller than the control plants. So I don't even have to do this data. I can do what's called a directionality check. Okay, so with a directional hypothesis, directional alternative, we can do a directionality check, which is just kind of a common sense check to see, does the data I have, could it even support what the alternative is claiming? Okay, and if the answer is no, you can stop. You can just say, I will have no evidence to reject the null. If the answer is yes, could the data I have even support the alternative? If yes, then carry out the test. Okay. And the key here is that we're supposed to come up with our alternative hypothesis prior to looking at the data. So if we have a hunch that ANSI plants should be taller or shorter than the control plants, that's fine, if you have some kind of suspicion. But if you look at the data and then you modify your alternative hypothesis so that it kind of matches what happens in the data, that could be considered dishonest, or what's known as p-hacking, okay? Where you're just trying to manipulate the question you're asking so that you get a significant result. Because as we saw earlier, when we had a non-directional alternative, we came to a conclusion where we did not reject the null. Okay, if we when we used the non-directional test. But with a directional test, same data, if we change this to greater than 0, then our p-value became significant. And so you don't want to be dishonest. You want to, if you don't have an idea whether it should be greater or smaller, use a non-directional alternative. If you have a suspicion that it should be greater, it should be smaller, then go ahead and use a directional alternative. But then if your suspicion turns out to be wrong, then you better say, oh, I'm not going to have evidence to support this alternative. Are we okay with this? All right. So I have two couple more topics to cover. Okay. We have, so I'm going to do one section in Chapter 8 because it's very closely related, and we're going to skip the rest of Chapter 8. Chapter 8 is all about paired data. Okay. So the example that we covered with Ttest was for independent samples. Okay, so we said we have the control plants and the ANSI plants, and the measurements from the control plants should have no bearing on the measurement of the ANSI plants. Okay, this group and this group, the measurements we take from each one, they have no bearing on each other. Okay. Sometimes we have situations where that's not the case, and so here we consider the possibility of having paired data. Okay, and this is at Chapter 8, Section 2. Okay, and so a common scenario is having before and after data. Okay, so let's say somebody marketed a magical weight loss pill. Okay, and so we look at before weight and we look at after weight. Okay, and let's say we had 6 people try this out, and their before weights were 240, 210, 170, 290. I'm going to run out of space. Okay, just 5 people. And 280. Okay, and after using this weight loss pill, this guy weighed 235, 205, 165, 285, and just for a little variation, we'll say 273. Okay? So if you look at this data, this was person A, B, C, D, and E. Does it seem like this magic pill works? Yeah. I mean, it's not... we're not having drastic weight loss, but it seems like everybody's losing about 5 pounds across the board. Okay? If we did a t-test on this, though, what would happen is that we would get an insignificant result. Okay, and I could conduct this in R. And the way to conduct a t-test in R is actually very simple. You create a vector of values. So here I would say before is 240, 210, 170, 290, 280. And then after, I'm going to store these values will be 235, 205, 165. Okay, and so I can get the mean before.
209.
Did I put 209?
Yeah.
Oh, instead of 290? Oh yeah, that's going to make a difference. Is my after correct? 235, 205, 165, 285, 273. Okay, so so the mean before weight, oops, is 238. And the standard deviation of the before weights is 49.7. The after is 232.6. And the standard deviation of after is 49.28. And then to do a t-test, you just do t-test before, after, and then that does a two-sided test. Okay? If we want to, what we should do is not a two-sided test or a non-directional test, but what should we say? So currently, okay, so if we treat this as independence, okay, so this is, maybe I'm going to just write this is the wrong way to do it, would be to treat before and after as independent samples. Because in this case, we would have mu1 minus mu2 equal to 0, and our alternative would be what? Mu1 minus mu2. If we did it directional, it should be that the before minus the after would be greater than 0, okay? Because we're hoping, does this magic weight loss pill work, right? Does the weight loss pill work? Okay, that's what we want to know. So we're expecting the after to be smaller than the before. Okay, so here I would write alternative is equal to greater. That before minus after is greater than 0, and so in this case I have 0.4337. Okay, so my p-value ends up being 0.4337, and so I get a I would come to the conclusion not to reject. The weight loss, we do not have evidence that the weight loss pill works. Okay, so this would be this is the wrong way to do it. Okay, what's happening here, the reason why we're coming to this conclusion, even though when we look at our data, it looks like across the board everyone's losing around 5 pounds or more. What's going on there is that the inherent variation, the variation of starting weights, is so drastically different from each other that the difference between the before and after, this about 5 pound difference, gets lost among the variation between people. Okay, and so the correct way to handle this would be to treat them as paired data. Okay, and so what this requires is we create a difference column. We do before minus after. And here we see a 5 pound difference, a 5 pound difference, a 5 pound difference, a 5 pound difference, and a 7 pound difference. And we want to know, is the difference we observe not 0 or greater than 0 in our case? Okay, so here our y bar, okay, so our difference is before minus after. So the difference I have is 5, 5, 5, and 7. The mean difference is 5.4, and the standard deviation of the difference is 0.8944272. Okay. So here we actually write a different, so my mean is 5.4 and my standard deviation is 0.8944. Okay. Here my null hypothesis and alternative hypothesis is actually different. My null hypothesis here is the mean difference is equal to 0. Maybe I'll just write lowercase d. Okay. And then the alternative is that the mean difference, because we have a directional alternative, would be greater than 0. Okay. So here we're treating it as paired data. So it's important that when you have paired data, you don't have mu1 and mu2. You only have the mean difference, okay? And so with paired data, you create your difference column, and then you ignore the other two columns, okay? So here we create our difference column, and ignore the other columns. Okay. And so our test statistic here would be the observed difference we see, which would be d bar. Under the null hypothesis, we would expect a difference of 0, and then we would divide by the standard error. Okay, so because it's minus 0, it just goes away. So we got d bar over the standard error. The standard error for d bar is the standard deviation of d bar. Or, I'm sorry, not the standard deviation of d bar. It's the standard deviation of d divided by the square root of n, in this case, how many samples we have, how many differences we have. So here we would have 0.8944 divided by the square root of 5. So the standard error here is 0.8944 divided by the square root of 5. And I would get basically 0.4 here. Okay, and so my test statistic, plugging that in, gives me 5.4 divided by 0.4. I get a very large test statistic. I get 13.5. Okay. And so if I were to look this up in the t-table using just the directional side, my p-value, so, you know, we look up 13.5. How many degrees of freedom? It would be n minus 1, because I don't have 2 samples anymore, I just have 1 sample. So how many degrees of freedom do I have? 4. Okay, so I would have 4 degrees of freedom. Look up 13.5. So coming up to 4 degrees of freedom. Oops. Looking at 13.5, we see we're beyond 8.6. 13.5 is way out here. So that means whatever our tail is, it must be less than 0.0005. So here we say our tail is less than 0.0005, and that would be our p-value because it's one tail. We don't need to worry about doubling it or anything. So our p-value is less than 0.0005. So we conclude that we have evidence to show weight loss pill effective. Weight loss pill is effective. It's okay. This can be conducted in R using Ttest before, after, alt equals greater, and then I'd say paired equals true. Okay, and so when I do it this way, I get my T is equal to 13.5, degrees of freedom is equal to 4, paired it says is 8.7 times 10 to the negative 5, and so we pretty much have everything matching here. Is that okay? For your benefit, I will put in the commands I've typed. So that's the wrong button. Okay, so I'll save this also. Okay, do we feel okay with the difference between a paired and an independent samples t-test? Okay, so in the, you're gonna have to read and try to figure out what's a paired data test and what's an independent data test. Basically, if there's reason to believe that sample 1 is connected to sample 2, and usually before and after is the most common scenario, but if there's a reason to believe that they have some kind of connection, then do a paired test. Otherwise, treat them as independent. Okay? If you have 2 different sized groups, then it has to be independent samples. Okay? If sample 1 has 10 and sample 2 has 9, those are definitely independent samples, because paired requires that they have that every data point in sample 1 is paired to a data point in sample 2. But just because two groups have the same number of data points doesn't make them paired. There has to be some kind of reason to believe that that the data points are connected to each other. Okay, with our last 15 minutes here, I want to talk about the relationship between hypothesis testing and confidence intervals. And I have several questions related on the quiz related to this topic. So it's good to learn. Okay, so confidence intervals. Hypothesis tests. alpha. Okay? So here's the main idea. Okay. For independent samples, conducting a hypothesis test with significance level alpha and a non-directional hypothesis, non-directional alternative is equivalent to creating a 1 minus alpha confidence interval. For mu1 minus mu2. So what does that even mean? I'll let you guys write that down. But basically, a 95% confidence interval is the same, or will lead to the same conclusion as a non-directional hypothesis test with alpha equal to 0.05. And likewise, a 90% confidence interval will lead to the same conclusion as a non-directional hypothesis test with alpha equal to what? 0.10. Okay? And you can extend that to any combination of hypothesis tests and confidence intervals. So how did we make conclusions with confidence intervals? So with confidence intervals, with a confidence interval for mu1 minus mu2, we said there is evidence of a difference between mu1 and mu2 if our interval, what? If our interval had this property, we would say there is evidence of a difference between mu1 and mu2. You guys remember? If our interval does not contain 0, right? So if our interval is entirely positive or is entirely negative, so if our interval does not contain 0, then we would say there is evidence of a difference between mu1 and mu2. Okay? And on the other hand, we would say you know, there is no evidence of a difference between mu1 and mu2 if our interval contains 0. So, you know, if interval contains 0, we have no evidence of a difference. All right, let's think about our hypothesis test. Okay, with a hypothesis test, we would come to the conclusion. I'm going to flip. Can I flip it to the next slide? Okay, so for a hypothesis test, we say we have evidence that mu1 does not equal mu2 if what? If our p-value is less than alpha, right? Is that okay? How do we know when our p-value is less than alpha? Okay, if our p-value is less than alpha, when our test statistic is greater than what? Than the critical value listed in the alpha divided by 2 column. So if alpha is 5%, basically if our test statistic, if we go to the 2.5% column, if our test statistic is greater than that, then that means the amount in the tail is going to be less than 2.5%, which means our p-value is going to be less than 5% when we combine both tails. Okay, and then the flip side is also true. Okay, we say no evidence that mu1 doesn't equal mu2 if p-value is greater than alpha, which is the same thing as saying test statistic is less than the critical value for alpha over 2. The critical values for here, critical value for alpha over 2, are the same critical values that we use in our confidence interval. You can even verify that. If you look at your t-table, the critical values for 95% correspond to the critical values for basically alpha over 2. The critical values for 90% are the same as the critical values for 0.05. And so the conclusions we make from a confidence interval are exactly the same as the conclusions we make from a t-test. So let's try a couple brain twisters out, and then I'll let you guys go. So let's say we've gathered data. We gathered data, and we performed a hypothesis test with alpha equal to 0.05. And let's say, I'm not going to give you any more information. I'm just going to say the conclusion made at the end of this test is that we do not have enough evidence to reject the null hypothesis. Okay, so basically not enough evidence to say there is a difference between mu1 and mu2. So just so you know, you're going to see some questions on the quiz almost the same as this, just slightly different, okay? So you can start this in your notebook. Okay, so here's a couple questions. If we did the exact same test, with the same data, but had used alpha equal to 0.10 instead, what would have happened? Or what conclusion would we have made? Okay, and your choices are reject the null, do not reject null, or not enough info. Okay, and then I'm going to ask the exact same question, except instead of alpha equal to 0.10, I'm going to say alpha is 0.01. So the only thing here, different here, is that alpha is 0.01. Okay, so exact same question. Can you answer either of these? Okay. Do you need a minute to think about this, or do you want me to just give you the answer? Huh? Okay, so well, let's think. Okay, so here, what does this statement tell us? We performed a hypothesis test with alpha equal to 0.05, and the conclusion we made is that we don't have enough evidence to reject the null. So what is the one thing we do know about our test here? We can say something about our p-value. We can say we know our p-value is what? We know our p-value is greater than 0.05. Okay, so if we know our p-value is greater than 0.05, if we conducted the same test again with the same data, we would come to the same p-value at the end. And if we compare that same p-value to alpha equal to 0.10, is that p-value bigger than 0.10, smaller than 0.10, or we don't know? Here we don't know, so here we write not enough info. Okay, because we don't know if our p-value is bigger or smaller than 0.10. Okay, same question, same data, same everything, but now alpha is 0.01. Do we know if our p-value is bigger or smaller than alpha? We know it's bigger. We know our p-value is bigger than 0.05. We know it's bigger than 0.01. So in that case, we would what? We would do not reject the null. Is this okay? Okay, I'm going to copy the just the heading onto the next slide. You don't have to copy this. You rewrite the heading, okay, obviously, because it's in your notebook. We're going to do the same thing, okay, and this time we're going to write, okay, if I make a 95% confidence interval, will the CI contain 0? If I make a 99% confidence interval, will the CI contain 0? And if I make a 90% confidence interval, will the confidence interval contain 0? Okay. The answers, your answer choices are yes, no, or not enough info. So for each of these, you just have to think this is equivalent to doing a hypothesis test with what? Hypothesis test with alpha equal to 0.05. This is the same as a hypothesis test with alpha equal to 0.01. Hypothesis test with alpha equal to 0.10. So the hypothesis test with alpha equal to 0.05 would came to what conclusion? Do not reject, right? So do not reject means, does it contain 0? If we have no evidence of a difference, that means our confidence interval contains 0. We don't have evidence of a difference. A 99% confidence interval would then what? It would contain 0 also. Because at 0.01 we would not reject, which means our confidence interval would come to the same conclusion, meaning it could contain 0. 90% confidence interval, same thing as alpha equal to 0.01, or 0.10. So this we said not enough info, and that would be the same over here, not enough info. Visually speaking, we can think of confidence intervals. So if our 95% confidence interval contains 0, a 90% confidence interval is wider than that, so that will also definitely contain 0. A 90% confidence interval is more narrow, so now we're not sure if we still contain 0 or not. Okay? So study these, think about these things, and we'll see you guys next week. There is a quiz. The details of it will be posted online. Is there a lab? I don't.
It is on the syllabus.
I want to say no. Okay.